everyone, I'm Yigong from Johns Hopkins University. Today, I will present the work, Automated Reasoning and Detection of Species Configuration in Large Systems with Symbolic Execution. This work is done with Gongqi Huang and my advisor, Huang. When we use some system software today, it is common to see the software provides a complex configuration file like this, which consists of hundreds of parameters controlling different aspects of the system behavior. Users have to set these parameters properly. This can be a very challenging task, and the users inevitably introduce misconfiguration that leads to system failures. The problem of system misconfiguration is severe enough that many works have been proposed to help administrators detect misconfiguration. These works mostly focus on detecting invalid settings introduced by average users who are not familiar with the software. But a lot of real-world misconfigurations are settings that are valid, look benign to experts, and do not cause obvious failure symptoms in testing. But when the settings are rolled out to production, they cause catastrophic performance degradations. For simplicity, we call such settings species configuration. So, let me walk through an example. One day, Bob received many users complain that it is too slow to load the drop-down UI on his website. After some profiling, Bob found that some circle queries are too slow. However, there's no data partition in the table and the log looks good. So, Bob asked on Stack Overflow, and someone pointed out that the issue might be caused by inaccurate cost estimation. Bob then checked the configuration file and looked through all the settings for estimation cost. Finally, he found that the default settings for page read cost would cause join queries to choose a slow execution plan. This problem is triggered because of recent changes in the front end that generate many join queries. Due to this settled performance effect, many species configurations cause severe performance issues in production systems. Current tools only solve half of the problem. Black box testing has limited code coverage, and the results are tied to the environment. Administrators often have more questions. For example, they want to know what will happen if I change the setting from X to Y, or the scale changed to 100 nodes. To answer these questions, we need an analytical approach to systematically reason about the performance effect of configuration. We present an analytical tool called Violet. Violet works in two steps. First, the Violet systematically explores performance effect for all valid settings. It makes the configuration and its input symbolic. Then, by symbolic execution, Violet can derive a comprehensive performance cost model for each configuration. Second, give a concrete input target parameter and other parameter. Violet can make a quick judgment about whether it would cause performance regression or not based on the impact model. It can also answer more detailed questions asked by the system administrators. Before describing our solution, we first summarize several common code patterns of how species configuration affect performance at code level. In the first pattern, the value of the parameter causes the system to execute some costly operation. In this case, setting the autcommit parameter to true can trigger an additional fsync syscall. In the second pattern, the configuration incurs additional synchronization. For example, the configuration would free the query cache and cause subsequent queries to open the table and try to acquire log. Although the additional synchronization itself may not be expensive, the system concurrency is decreased. Also, since the cache is invalid, the parameter forces the execution flow to go to a slower path, which fetches the data from the on-disk table instead of from query cache. The final pattern is frequent crossing threshold. For example, if the log buffer size is too small, the system would frequently flush the block buffer to the disk. Given these findings, one potential analytical approach is to use static analysis, but mapping these high-level patterns to specific code requires a lot of domain knowledge. Also, there are other patterns and many variants that can be missed. It is also difficult to estimate the performance statically. But we found, despite the variety, the general characteristic is that the special configuration drives the system to execute some code passes that are significantly worse than other passes. The performance effect is also dependent on other parameters, input and the environment. With this finding, we can transform the problem of detecting specious configuration into two sub-problems: finding slow execution paths and deducing the triggering condition for the slow path. Thus, Violet takes a symbolic execution approach, which allows us to analyze system code without being limited by code patterns, explore all feasible paths, measure concrete performance, and deducing the triggering condition. In the following section, I will show how does Violet derives this performance model in large systems. Violet takes the system code as input and adds a hook to automatically make configuration symbolic. It has a static analysis to assist the discovery of dependent parameters. Violet symbolically executes the target programs and the tracer records the performance result for each path. Finally, the Violet trace analysis builds the impact table from the raw tracing data. First, I will talk about the symbolic hooks. The simplest way to make configuration symbolic is to make the whole configuration file symbolic. However, this would cause path explosion due to the complexity of file parser implementation. We found that the system usually keeps a dictionary to map the configuration to variable, which helps identify the program's variable corresponding to a parameter. But we also need to know other information like type, ranges, and default values. We take a simple approach that inserts a hook function to iterate through the dictionary and make the variable symbolic. Here is an example for hooking MySQL. After the MySQL parser function, we add a hook to iterate all the variables in the dictionary and implement make symbolic function to make different types of variables symbolic. By doing so, we can easily make any configuration symbolic. Then I will talk about static analysis. With symbolic hooks, the next question we ask is which configuration we want to make symbolic. The straightforward way is to make all the configurations symbolic. However, it would cause path explosion since there are too many configurations and it would waste time to execute some costly operation that we are not interested in. Also, the output data might be misleading. Think about this case. If we want to understand the performance effect of autcommit, the OPTC is irrelevant because no matter what value of OPTC, it doesn't impact the performance effect of autcommit. If the task 1 is a very heavy operation, the symbolic execution might waste a lot of time on executing task 1. It can become a serious issue and cause the system get stuck at the very beginning. Moreover, even the system finished execution, the result would contain a misleading one that OPTC is 1, which should not be a precondition for bad performance. Thus, we need to find the related configuration and only make them symbolic. A related configuration is a configuration whose usage point is in some execution flow of the target configuration. This definition is similar to control dependency relationship, in which X is control dependent on Y if X execution depends on a test of Y. Thus, we can detect the related configuration by finding the control dependency first. However, there are some scenarios that the related configuration is not control dependent on target configuration. For example, OPDC and flush at TX commit is related to autcommit, but flush at TX commit is not control dependent on autcommit since there's OPDC in between. Thus, we need to relax the definition of control dependency to X depend on a test of Y and other parameter. With the definition, we can detect related configuration in 2 steps. First, we compute the enabler parameter set of the target configuration. Then, we compute the influence parameter set for the target configuration. The union of both sets is the related configuration. For more detailed information about the algorithm, you can look at our paper and technical report. Now I will talk about Violet tracer. The main requirement for tracer is that it shouldn't incur high overhead because the overhead would be reflected on the profiling result and cause inaccuracy. To meet this requirement, we adopt 3 general principles in our system design. First, we try to use low-level signal to capture performance data. Second, we defer expensive computation to the end of each pass. Third, we avoid memory-related operation if possible. Here, I will show how does Violet trace the latency. To trace the execution time of F2, Violet captures the call signal of F2 and appends the current timestamp as well as EIP and the return address into the call list. Similarly, it captures the return signals and appends it to the return list. With the EIP and the return address, we can find the corresponding call return pair and defer the reconstruction of the call stack at the end of each pass. Besides the latency and call stack, we also trace other metrics like the number of instructions, system call, and etc. We call them logic cost metric. The reason that we need to trace logic metric is that some special configurations are not obvious in latency but can be captured by logic metric. Also, the logic metric are independent to the environment and can be used as a general metric. Finally, I will talk about the Violet trace analysis. By making the configuration symbolic, we can systematically explore all the possible settings and record the performance cost. For example, in this case, we have 2 parameters, autcommit and flush at TX commit. We first fork at the branch with autcommit equal 1 and not equal 1. If the autcommit is not equal 1, we trace the cost as X. Then we fork on flush at TX commit equal 1 and found this branch has a costly operation. After we trace all the possible parameter combinations, we can derive the performance model for each constraint and found that there's one slower path with the condition autcommit not equal 1 and flush at TX commit equal 1. The Violet tracer compiles each pair of the paths. If it found one path is extremely slower than other paths, it marks the slower one as specious configuration. But some path comparisons aren't very meaningful. For example, if we compile the second row and the fourth row in the table, while we can find the fourth row is bad, but we can't know which configuration parameter is the root cause. To get more meaningful results, Violet uses a similar path first comparison. It will compile the path with the most similar constraint first. If the constraint for a related parameter appears in both states, we will add 1 to the similarity score. If 2 paths don't have any common constraint, we will not compile them. Violet is built on top of S2E, a state-of-the-art symbolic execution platform published in ASPLOS 2011. The tracer is implemented as S2E plugin, and the Violet static analysis is built on top of LLVM. To mitigate the path explosion and complex constraint, we use selective symbolic execution, which will silently concretize variables before library call or syscall. It is accurate, but it will lose completeness. In order to achieve high completeness, we relax the concretization rule For more information, please look at our paper. Now I will talk about the evaluation. For the evaluation, we would like to answer three main questions. How effective is Violet in detecting special configuration? How useful is Violet? What is the performance of Violet? We evaluate Violet on 4 popular systems: MySQL, PostgreSQL, Apache, and Script. Each one of them have hundreds of thousands lines of code and hundreds parameters. The last column shows the lines of hook we added for each system. As you can see, we only add less than 200 lines of code for each system, which is a very small amount of manual effort. We first evaluate Violet on 17 known cases that we manually collected. The Violet can detect 15 of 17 cases. We then use Violet to detect new special configuration. We define special configuration as the configuration whose default value would cause performance regression, and there's some performance impact that is not documented in the official manual. Violet found 11 cases, 8 of which are confirmed by the developers. Among these cases, Violet found some unexpected parameter combination that leads to bad performance. For example, the parallel lead participant is used to control the parallel query. It seems not related to the page read cost, but some combination of parallel lead participant and random page cost would cause some join queries to choose a query plan that wastes system memory. We also conduct a coverage experiment which tries to derive performance model for as many configurations as possible. The result shows that the Violet can derive performance model for 53.9 of the configuration. We finally test the analysis time for 471 parameters in coverage experiment. We found that the median analysis time for MySQL, PostgreSQL, and Script is less than 10 minutes, and for Apache, the median time is less than 20 minutes. Our work built on top of advance of related work in misconfiguration detection, diagnosis, and performance tuning. The differences between performance tuning and our work is that the performance tuning tries to improve the performance of suboptimal configuration to optimal configuration, while our work is trying to prevent severe performance regression caused by specious configuration. In summary, specious configuration is a common problem and difficult to be detected due to its subtle effect. We advocate systematically reasoning about its effect from the source code. We built an analytical tool, Violet, to detect special configuration in large systems with symbolic execution, and Violet can detect 15 of 17 known cases as well as 11 new cases. That's all for my talk. Thank you all for listening to this talk, and I'm happy to take any questions.